Look at this screen. Without context, raw network traffic appears as a chaotic stream of hexadecimal noise rushing across your monitor. But to successfully use security analysis tools like Wireshark, you have to read the underlying language dictating how that data moves. That language is made of network protocols. These are the discrete, nested rules governing exactly how data is encapsulated, packaged, and transmitted from one machine to another. When the foundational architecture of the Internet was designed, the primary objective was simply getting machines to talk to each other. Security was a secondary concern. Because the priority was pure connectivity, the system relies on deep structural assumptions of trust between devices on the network. Decoding these nested layers and exposing where those trust assumptions break down provides the technical basis for identifying vulnerabilities and executing network exploits. Any digital routing starts with a logical backbone, the Internet Protocol, or IP address. Every device connecting to the Internet requires one. The limitation of the current IPv4 system is that it only contains about 4.3 billion unique addresses. With over 8 billion people using multiple devices, the math fails. To solve this scarcity, network architects created private internal subnets, where a local group of IPs can be reused infinitely, isolated from the wider Internet. When a device joins one of these local networks, the Dynamic Host Configuration Protocol, or DHCP, temporarily leases an internal address. This local topology maps internal device nodes to a central router, running network address translation. When a machine communicates outward, the router swaps the private internal address for a shared public IP using a lookup table. For return signals, the router checks the table, matches the public data to the private IP, and sends the packet back to the local node. Inside that local boundary, devices communicate strictly across the physical hardware of an Ethernet network. This diagram shows nodes linking logical IP addresses to physical MAC addresses using the Address Resolution Protocol, or ARP. To find a destination MAC address, a computer sends an ARP broadcast wave to every node asking who owns the IP. The target node then returns its distinct MAC address signal. The architectural flaw here is that ARP requests and responses completely lack authentication. An attacker can weaponize this using reconnaissance tools like NetDiscover to flood the network with gratuitous ARP requests, forcing every internal system to reveal itself and map the entire local topology. Because the protocol blindly trusts any response it receives, attackers can spoof identity signals. By telling the network that their machine is the router, they intercept all local traffic, executing a man-in-the-middle attack. To move data successfully across these networks, it must be explicitly packaged at the transport layer using IP and TCP headers. This block diagram of an IP header acts like a packet's ID card. If a packet is too large, the fragment offset row dictates how it is split apart. Attackers manipulate these offsets to slice malicious payloads into irregular pieces, slipping past perimeter security. IP provides the destination, but the Transmission Control Protocol, or TCP, is paired with it to guarantee that data is delivered reliably and in order. In row 4 of this TCP header diagram is the flags field. These flags dictate the connection state. SYN initiates, FIN closes, ACK acknowledges, and RST hard resets. By firing a specific sequence of SYN or RST flags at a target, network mapping tools can silently map open ports or elicit errors to reveal vulnerabilities. Another critical metric in the TCP header is the window size field, which manages packet buffering and flow control. Different operating systems assign distinct window sizes. By analyzing this single field, an attacker can predict the target's operating system with roughly 80% accuracy. TCP achieves this reliability by operating as a stateful protocol. It enforces a strict connection mechanism requiring mutual verification before any real data is sent. This state machine diagram illustrates the TCP three-way handshake. The client initiates the connection by sending a discrete SYN signal line to the server. The server responds with a SYN ACK signal, and the client confirms with a final ACK. Only then does the connection lock in. Contrast this heavily verified process with the User Datagram Protocol, or UDP, which is entirely connectionless and stateless. In this diagram, UDP completely discards the handshake and verification process. It fires data packets across a single, unacknowledged path, prioritizing speed over delivery confirmation. While UDP does not guarantee delivery, its low overhead makes it the mandatory transport layer for fast-moving critical infrastructure, like domain name resolution. The architectural choice between TCP and UDP is a direct trade-off between verifiable security and necessary speed. This structural difference dictates how analysts configure tools. Once the transport connections are established, we move up the protocol stack to the application layer, serving actual user data. A core protocol here is the Domain Name System, or DNS. It operates as the translation service, converting human-readable URLs into routable IP addresses. If an attacker has already gained access to the local network, they can exploit this translation process by spoofing DNS responses. Watch how this translation request is intercepted mid-path. Instead of resolving to the correct IP destination, the spoofed response reroutes the client directly to a malicious, attacker-controlled local endpoint. Another application protocol is Server Message Block, or SMB, which operates over TCP/IP to share files, printers, and resources across the network. SMB has an extensive history as a primary source of critical vulnerabilities in enterprise environments. Vulnerabilities in SMB often allow attackers to execute remote code with full system privileges, turning simple resource sharing into total machine control. For infrastructure management, networks rely on the Simple Network Management Protocol, or SNMP, to monitor the health and performance of connected devices. A breach of SNMP grants an attacker total visibility. They can map local topographies, manipulate router configurations, and decrypt VPN traffic. Automated management systems are not the only risk. Legacy, user-facing application protocols like Telnet present structural dangers. Here is the fatal architectural flaw of Telnet. As you see on this transmission line, all data, including login credentials, is sent in readable plain text, easily duplicated and intercepted by a third-party observer. Early versions of HTTP functioned on a similar message-based architecture. It relied on TCP for reliable transport, but inherently lacked encryption. Relying on legacy, unencrypted application protocols practically guarantees credential interception. This vulnerability forced the modern cybersecurity shift toward encrypted channels like Secure Shell. Ultimately, a routable network packet is simply a nested hierarchy of these individual protocols acting in sequence. In this diagram, application data is wrapped inside a TCP header, then an IP header, and an Ethernet frame. Captured, this encapsulated packet translates directly into the row-by-row analytical interface you see in a dashboard like Wireshark. Network analysis and offensive security aren't derived from writing arbitrary code. They come directly from exploiting the highly predictable state machines built into these protocols. Mastering these header structures, from ARP's blind trust to TCP's precise flag mechanics, provides the architectural blueprint required to manipulate network traffic and secure modern systems.